Hello, in this video we are introducing the Climate Change Adaptation Digital Twin. We'll give you an overview of the system, the available simulations, including an evaluation and how to access the data. Destination Earth is a flagship initiative of the European Commission to build a digital replica of the Earth system. It is implemented by ECMWF together with ESA and EUMETSAT. ECMWF is building the digital twins, one of them the climate digital twin, as well as the digital twin engine. EUMETSAT is providing the central data storage facilities for Destination Earth, the Destination Earth data lake. And ESA is building the Destination Earth platform, which allows users to access the information provided by Destination Earth. So in this presentation, we'll focus just on the climate DT. The Climate Change Adaptation Digital Twin is building an operational framework for kilometer-scale multi-decadal climate projections. The main features are that we have a regular production as well as the possibility to introduce frequent updates to the models and the simulations that we're providing. So a well-defined framework allows us to have enhanced flexibility of simulations and outputs to respond to user needs. One of the key aspects of Destination Earth is the enhanced spatial and temporal resolution, and this enables two things. On one hand, high spatial resolution means we're directly simulating the processes that are relevant for climate change on a local scale, but also by having high-resolution information as an output, this allows a direct integration of impact sector models into the digital twin workflows, which means we're producing climate data and climate information side by side. The Climate DT is built together with the European partnership, crossing supercomputing centers, national met services, as well as research institutes. The type of questions that we can answer with the Climate DT system is, for example, if we look at the wind energy sector. Knowing that storm occurrences might shift under climate change, we can ask, where should we build the next wind farms so that we are prepared for the climate change to come in the next decades? What you see on the left is a visualization of temperatures and winds. And below the red line, you can see the resolution of the climate DT, which is 5 kilometers globally. Above the line, you see the typically available resolutions from current state-of-the-art climate models that are closer to 100 kilometers. And you can clearly see that we're representing a lot of the fine-scale structures in the wind patterns that are relevant if you want to investigate potential wind farm locations. So in the next few minutes, I want to take you through the operational framework for building and running these simulations. So it all starts with the climate models. These are 3 different global climate models, IFS NEMO, IFS FESOM, and ICON. They are running on the EuroHPC supercomputers and are producing a homogenized data stream. So all of the models are producing exactly the same output parameters and provide them on the same grid. This is then written into a database on the HPC system. And then 2 things are happening. On one hand, we have an online monitoring and evaluation, which is running while the simulations are progressing. And so this allows the operators and scientists to check the progress and evaluate the results of the simulations while we produce the runs. What we can also do is we have a streaming to impact sector models, and this is also happening in the same production workflow. And I want to show you what this means with coming back to the wind energy example. So in this animation, you can see the wind speeds as they are simulated by one of the Climate DT models. we can then use an impact sector model to translate the wind speed simulated by the climate model into actionable climate information, for example, the capacity factor. So a capacity factor explains how much energy is being produced by a wind turbine given the wind speeds that we get from the climate model. A high capacity factor means we produce energy near sort of the maximum capacity of a wind turbine. A low capacity factor means the energy production is much lower than the potential energy production. And this can happen for several reasons. For example, if we have low wind events, then of course the wind turbines are producing less energy. But also during high wind events, wind turbines have to be shut down to prevent damage, which also results in lower energy production. Now, with the high spatial resolution, we can then zoom into a specific location. For example, here for an actual wind farm location off the coast of Scotland. And as the climate DT is simulating the wind speed, we directly compute the capacity factor for a wind turbine in this location. And as the simulation is progressing, we can then accumulate statistics from week to week, season to season, or even decade to decade to see how wind speeds and energy production are changing over time. Now, in the workflow, we have several impact sector models directly embedded. This is covering several sectors, not just wind energy. Now, as a next step in the production workflow, we then move the simulation output to the destination Earth data lake. And so this is then making this output available to users via the destination Earth platform, where you can find different ways to interact with the data, either via Jupyter Hub or also via interfaces provided by various applications and use cases. And we'll explain the data access in more detail later on. We are providing two types of simulations. First, the multi-decadal climate simulations are starting in 1990 and are using historical forcing from CMAP6. From 2015 onwards, we are following the SSP 370 high emission scenario until 2050. These simulations are run with 3 climate models, IFS NEMO, IFS FESAM, and ICON, at 5 kilometers global resolution. We also have the control simulation. This is an experiment where we have constant 1990 forcings for at least 10 years, and this allows us to quantify artificial drift in the model. The second type of simulation that we provide are the extreme event storylines. These allow us to replay weather events from the recent past in a colder and warmer climate. So we have the present day conditions, then we have a past 1950 climate and a future 2-degree world. And these simulations are running with IFS FESAM at 10 kilometer resolution globally with 5 oscillonimbus. So overall, we have produced well over 2 centuries of 5 kilometer simulations and over a century of simulations at 10 kilometer resolution. So in the following, we'll now go into the details of these simulations and how to access the data.
I am Matthias Aengenheyster and I work at ECMWF in the Climate DT team. And I will look at the simulations a bit more in detail and show you how to access the data. As explained, we have the 2 types of simulations. The climate simulations, which are initialized and then forced with external forcing, and they develop their own weather and climate. And the extreme event storylines, where the difference is that the large-scale weather is constrained to observations from era 5 from 2017 to the present, but doing this in past, present, and future climate states. What this allows you is to look at particular events, how they could have played out in the past or in a future climate, because they're constrained to the exact same circulation. I'm showing you one example here of the Central European floods from September 2024 that caused a lot of flooding in Eastern Europe here with a focus on Vienna. So if I play this, you'll see that the same weather structure with a large-scale circulation evolves, but because of the colder world in the past and the warmer world in the future, the amount of precipitation changes. And this can be done for all weather events that have occurred since 2017 globally. And for your particular region of interest, you can look how this particular event could have occurred in the past or could be impacted by a warming world in the future. In contrast to the extreme event storylines, the free-running simulations are just initialized in 1990, forced with external forcing, and generate their own weather and climate until 2050, as shown here in a video done by my colleague, showing the extreme spatial and temporal detail generated with these three models. Having done these free-running climate simulations, it's of course essential to look at their performance, look at the climate they generate, and compare this to existing models, for example, as done in the CMIP and Cordex intercomparison projects. Already while the model runs, as was explained before, extensive analysis and evaluation is done in the so-called AQUA activity that creates a lot of charts looking at the mean climate and comparing them, for example, to CMIP. And you see one example here on the left, which is a so-called scorecard that compares the performance of, in this case, IFS FESUM to the CMIP 6 ensemble. Many of these charts are available for users with upgraded access on the Destiny platform. We can also look into this in more detail and put, for example, the evolution over time of the global mean surface temperature of the climate TT simulations compared to observations and the other global models. So here in gray is the CMIP 6 ensemble of like around 30 models. And in black and brown, we have observational data sets. Now we can put the climate TT simulations over this and look at this, and we can do this for many variables. And for example, here we see that the trend, the evolution over time of global mean surface temperature is captured very well in these simulations. They also have their own different biases. For example, here Icon is a bit colder, and we can do this for all the variables and understand their performance in detail. Of course, a key feature, as we have already explained, of these simulations is that they run at very high resolution, much higher than usual climate simulations. So we're looking at particular high resolution local features that represent extreme events and how our models can represent them compared to other examples. So here we're looking at extreme precipitation over the Alpine region, so looking at northern Italy, Switzerland, Austria, and southern France. And here we show this maximum daily precipitation averaged over 15 years from a number of observational products. Some of these are station-based, such as EOPS, some are reanalysis, such as AR5, and some are based on satellites. When we look at a field like this in typical climate simulations, such as the CMIP 6 multi-model mean, this field is very smooth, which is due to the fact that these models have lower resolution, and so their representation of the topography is just not as detailed. In contrast, Cordex, which runs regional models at much higher resolution, can really capture a lot of the interactions between the atmospheric circulation and the topography. And our climate TT simulations, running at 5 kilometers globally, also capture features at this kind of spatial resolution. Unlike Cordex, these are globally free-running simulations, so they don't depend on forcing from global lower resolution coupled models, and they have the same spatial resolution globally. I will now talk a bit about the data access. As explained, all the data is available in the Destination Earth data lake. The way it is accessed is primarily through a tool called Polytope, developed at ECMWF by many colleagues, and it mirrors quite closely the way data is accessed through MARS by submitting particular data request dictionaries, one example shown here. And Polytope has many features to exploit structures of the data and to efficiently retrieve full spatial fields, but also time series or cutouts over particular regions. For example, here over particular countries. Polytope is the main avenue to access climate TT data. Data access requires making an account on the Destiny platform and applying for upgraded access. Then a user can submit Polytope requests from anywhere and stream the data to their local system. The data portfolio is described in detail in the user guide. As a short summary, the ClimateT writes many variables, and it writes them both at high and at low resolution, and at hourly frequency as well as monthly means. This means that for many applications that use climate data, for example, just looking at the mean of global surface temperature, it is sufficient to work with low resolution monthly mean data. For a user, this means much less data that has to be streamed via the internet to the local system. Colleagues have created many examples and help us on how to interact with Polytope and to facilitate data requests. Many of these are available on GitHub under this link. I just want to highlight one of these here, the so-called ClimateT Explorer. This enables lazy browsing and generating of Polytope requests in the background. What it means is that the user does not have to think about the particular variable they want, look it up in the data portfolio, and then write a data request. Instead, they can open the entire dataset as if it was on a local system and then submit just a sort of load request, and the data request will be built in the background and streamed to the system, which should really facilitate interactive analysis of this dataset. All of these tools are in active development, so looking in the future, we look forward to new features. In conclusion, we've presented the ClimateT system, which provides local insight globally beyond the state of the art by performing multi-decadal 5-kilometer simulation and providing a high-resolution, high-frequency data for users for their particular applications. We are working on conceptualizing ClimateT within CMIP and Cortex simulations, which enables uptake and is essential for quantifying uncertainty and putting the ClimateT performance in a broader context. The ClimateT can adopt the latest scientific breakthroughs in operations, making them accessible to users. And Destination Earth is continuously improving the accessibility and interactivity of the system, working on new simulations, interactive visualizations, and for the simulations to be done in 2027, working to integrate CMIP 7 forcings to be up to date to the latest development in climate forcings. The up-to-date information can always be found on the Destiny platform on the ClimateT landing page, so please stay tuned there for any updates. Thank you very much.